And I think what I'm going to do is next week, we are going to what happened? Okay, yeah, okay. Why did it? What is this? Oh, okay, yeah. Let's see. So let's start with this two-stage MOSFET amplifier. Of course, the first most important step is to identify in the circuit which transistors are composing the actual amplifier and which transistors are the current source or current mirrors that provides the biasing for the circuit. So far we talk about this thing like MOSFETs, BJTs. There are two important things. One is the DC biasing. The DC biasing is the circuit has to work in like MOSFETs, they have to work in a saturation region. And for BJTs, they have to be in active region. So the DC biasing is important to make them work in those regions. If something happens, the biasing is changing, and then these MOSFETs will start to leave their saturation region. Therefore, you can no longer use the amplifier. Either into the trial mode or cutoff mode. Either way, your amplifier is no longer valid. So that's why you have an input range. For the small signal for amplifier, what we mean is that we always have a small AC input that is added to the top of the DC, and then so at the output, you can see like if you don't have a capacitor at the output, like next chapter we're going to look at the differential frequency response. That if you don't have a capacitor at the output, if you use a scope, many of these amplifiers, you will see a DC output added, AC added on top of the DC output. But if you want to get rid of that DC, you have two methods. You can add a capacitor. So the capacitor look like a short circuit for high frequency. Therefore, you only see the AC. On an oscilloscope, in fact, you can use you can measure DC only, AC only, or AC plus DC. So if you look at get rid of the DC offset, you will see AC only, right? So those are the two things that you have to look at. Is in any transistor circuit, or most of the transistor circuit, when we talk about linear electronics or digital electronics, most of the time we look at these two things. If you get to 584 to power electronics, they use the same symbols, they use similar transistors, but they use it in a different way. In power electronics, they call it switching power supplies. What do they mean? That they avoid the saturation range for MOSFET. They either in triode or in cutoff. For BJTs, they either in they're not in active. So this is like a switch when you turn it on or turn it off. Right? So that's something you guys have to learn in different class. We're not going to go to there. So in this circuit, if you look at the circuit composition, you will see that where they mark the plus and the minus, and often like they mark Q1, Q2, that's where you start look at. So this has the input, this is input, and these two are like a head-to-head. So this must be amplified. So that is a differential pair of amplifier. So we can circle that one. This is your differential amplifier. And so below that differential amplifier or above that amplifier, you know what happens. It's either the current source for biasing, or sometimes it's cascade amplifier or cascade mirrors that to increase the resistance of the circuit. So which means if you look at this two, these are back to back, which the gate is connected to the drain. So this is a typical current source. So this is a current source. Okay, so we have this one is a current source. We can circle that one, the current source. How about the one above? The one above is Q3 or Q5. If you look at Q5, and you're going to see Q5 and Q8, they are connected also gate to gate connected back to back. And then this is a very typical current source also. Of course, there's a reference current here, and this reference current can be built by something else, and we don't worry about this time. But think of like this is ideal current source you can use. So that's a current source over there. We have another current source. And the output of our amplifier, this is your output. And this output is connected to here. And this is your transistor. So apparently this is your, so this is connected here. So this is your amplifier. So this must be amplified. And how about the above one? Is the above one amplifier or is it a current source? So what you need to look at is there's the gate or something connected to an input. If you look at the gate, what happened to Q7 of the gate? It's connected to the gate of Q5, and Q5 is a current source. Therefore, Q7 is a current source. So this is your current source. And this is your amplifier. So this is your stage 2. And then this is your stage 1. Okay. So now you identify, okay, so stage 1 is a differential input, differential pair, and stage 2 is a single amplifier, and the output is at over here. The output is over here. So for this amplifier, what would you call? Is this a common source? Is it a common drain or the common gate? What do you see? It's a common source. Why is it a common source? Because the source is grounded. So you're taking output at the drain. And above the drain, there's a current source. So current source is kind of the load device for this amplifier. Okay. So now we identify all these components in the circuit. So now we are, oh, by the way, on this amplifier, remember, this amplifier is support for differential amplifier. Remember, we talk about you have a differential in, differential out, or you can have a differential in, single-ended output. So in this case, the Q1 also have this current source as a load. So therefore, this is differential in, but single-ended output. It's a single-ended output. It's not a differential output. So that's the arrangement for this circuit. Now for the next example, for the BJT, we'll see that you have differential in, and you have differential output as well. But for this one, it's a differential in and differential out. So for this type of circuit, what you can do is you can redraw the circuit so that will make your life a little simpler, is doing this. I'm going to draw the amplifier only. So this is a PNP type of amplifier. Minus plus input, and then the output of this one here is your output. Output is connected to okay. So for now we can use like a ground to ground all these things. Now I simply replaced all the current sources away, just leave the amplifier, so that will make our life a little easier to calculate the gain. So if you look at it this way, is that this is a differential input, but single-ended output, and this is a common source amplifier. So ultimately, this is very simple circuit, very simple circuit. And the gain, how do you calculate the gain? Well, since this is single-ended, but it has a current source. So for single-ended current source, remember, this gain can be calculated as basically for each of the current source, we have like a resistance connected to this ROY, and this is RO4. But see, this is PNP. So what type of amplifier is this one? Is it common source, common drain, common gate? It's definitely not common gate because input is at the gate. But since this is the PNP, So source is here and drain is here. So the source apparently is grounded, and then you have a common drain. You have a common source amplifier. So this what becomes your common ground, but this is where you have RO4 is your load. So this is your drain. So this is a common source amplifier. So this is RO6. So ultimately, if you go back to what we have learned before, you can easily find that A1 is going to be minus GM1 times RO2 in parallel with RO4. And you can calculate AO2 equal to minus GM6 times RO6 in parallel with RO7. And of course, your total gain A0 is AO1 times YO2. And after you calculating GM1, GM6, L1, L2, you can get the overall gain. But in this particular circuit, because each of the current source, that's why we do this in the past is when you have a current source at the drain. In this case, same thing, when you have a current source at the drain, it increases the load resistance by many, many times. So this RO7 is in the tens of kilo ohms, and this in the tens of kilo ohms, and therefore you had a really gain huge amount of gain. So we can continue to look at how much gain that we'll get. By looking at the circuit, I want to write this down so you guys can follow me. So we know that I reference was given at 100 microamps, and VT was given at 0.5 volts, and VA was given at 5 volts. We use this absolute value because there's a P, there's N-type. For N-type, it's a positive value, for P-type, it's a negative value. But when you do the calculation, it's the same thing. So you just use the absolute value or make it easier. And then they also give this mu N times COX, which is constant, is going to be 400 is microamp over V squared. But the P-type is a little smaller, is 100 mu amp times V squared. So that's the given value. So if we look at this one, I'm going to go back to the previous circuit, and you can tell me for the biasing, if this reference is 100 microamps, so apparently the Q8 is 100 microamps, right? And if Q8 is 100, how much is Q5? It's 100. And Q1, Q2, Q3, Q4, apparently they each divide by half. So you have 1, 2, 3, and 4, each are going to be 50 microamps. And how about this one? And Q7 is going to be 100 microamps, and this will be 100 microamps. And this is a suppose that each of them have the same area. But if the W and OL is different, and the current will be different. So you have to go back to look at what is so I'm going to write IQ8. So IQ8 is going to be IQ5 is going to be the same. It's going to be 100 microamps. But this IQ1 and IQ2 is going to be 1/2 IQ5. It's going to be 50 microamps, and which is also equal to IQ 3, IQ4. So I go back. So this one, because this is 100, so that's 100, that's 100. Q4 and Q5 and Q8 can match in the given condition, and Q1, Q2, Q4 each are half. So this is 50 milliamp, 50 milliamp, 100, 100. And then we'll look at Q7 and Q6. And Q7 and Q6 is going to be all these transistors, if they're matched as well. So we have IQ7, IQ6 are going to be 100 microamps, okay? So the next step is asking you to calculate. So that's number one, we got that current. And number two, they ask you to calculate VOV. Now remember, what VOV? How do we calculate VOV? We have VD equal to 1/2 K times mu COX it's mu CoX times WOL times VGS minus VT squared. Well, this VOV is equal to the over voltage VGS minus VT. So this is your VOV. So you from here, you can say that VOV equal to 2 times ID divided by mu CoX WOL and square root of this one. So all you need to do now is plug in this ID, because ID now for each transistor already found. From 1 to 8, we now know all the current. So we can plug in this current. And mu and CoX, depending on is NMOS or PMOS, this number either 400 or 100 micro. And WOL is also different. There's a table in the book. So we plug in each of this number, we can get a VOV. So fortunately, all the numbers were given that all the VOV is 0.2 volt. So it's very simple. You just plug in the numbers, you get it. And the way that they did it was by looking at, let me see. So by doing this, given the WOL, you can see the WOL, one is 10 divided by 0.4, the others are 2.5 divided by 0.4. So that's 4 times. So WOL is 4 times, but the mu times CoX is also 4 times. So that 4 and 4 cancels. That's why you got VOV is 0.2 volts. Okay. So once we got this VOV, and then we can get our VGS. So VGS from this equation over here. So VGS equal to VOV plus VT, which is 0.5, 0.2 plus 0.5, like 0.7 volts. So we get that number. So those are the DC, again, DC biasing calculations. We got this. So now we go to number 3. We go to number 4. That's number 3, yeah. So we go to number 4. Let's go to number 4. Number 4 is asking us to calculate GM. Now, we know that the GM equal to 2 times ID over VOV. That's for the MOSFETs. So this is 2 equations we got to remember by now. So 2 times ID times VOV. So VOV is 0.2, and ID is different for all the transistors. So therefore, GM is different for some of the transistors. But if you look at Q1, Q2, Q1, Q2, Q3, and Q4, so that GM will be 2 times 50 microamps divided by VOV 0.2. That gives you how much? Gives you 0.5 milliamp per volt. 0.5, right? 0.2, 100. Yeah, so 0.5 milliamp per volt. And then for that Q5, 6, 7, and 8, so that GM will be 2 times 100 micro divided by 2, 0.2 volts. So that will give you 1 milliamp per volt. So we got the gain now. So I mean, this is the gain is not actually the circuit gain, but it's the intrinsic the MOSFET intrinsic gain. And number 5, they ask you to calculate RO. Now we remember RO is VA over ID. So that's for MOSFETs. This GM and RO for MOSFETs and BJTs are slightly different. So we have to be careful. So don't make a mistake. So RO is VA, then VA is given at 5 volts. And ID is either 0.5 or 1. So if we take 0.5 milliamps, we're going to get 10, 5, no, oh, sorry, not 5. No. Here is not 5, not 0.5, 0.05, 50. So it's 0.05. Yeah. So 0. 0.05 milliamps. So it's give you 100 kilo ohms. That's for Q1 to 4. And then that RO would be equal to 5 volts divided by the other is 0.100 milliamps. So that gives you 50 kilo ohms for Q5 to Q8. So that's RO. So all these numbers are fairly easy to do. And then by number 6, what we need to do is to find the gain. Now the gain already, I mentioned earlier already. So the gain for the first stage is going to be GM1 minus GM1 times RO1 or RO2 in this sense, in parallel with RO4. So we already calculated our GM1 is 0.5, and RO2 and RO4 each is 100 kilo ohm. So it's this. So 50 to 50, 100K in parallel gives you 50. So 50 times 0.5, that gives you minus 25. So the gain is always volt per volt. It's amplification. So volt comes in, volt comes out, right? So that's volt per volt. And A2, it's going to be minus GM. The second stage, what's the number of the second stage? Second stage is Q6. So it's going to be GM6 times RO6 in parallel with RO7. RO7 is the load. So that gives you minus 1 times 50. I think it's 50, right? We calculate the number is 50 times 50, or in parallel with 50. But 50 to 50, so it gives you also minus 25 volt per volt. So your A equal to A1 times A2, which is 25 minus 25 times minus 25 gives you 625 volt per volt. So this two-stage amplifier gives you amplification rate of 625. So if you get 1 millivolt coming in, the output will be 625 millivolts. If you get 10 millivolts coming in, how much voltage output? If the input is 10 millivolts, 625 times 10, it's going to be 6.25 volts, 6,000 millivolts. Now, is it possible? So that's why the problem sets always ask you, what is the maximum power output? What is the maximum output as the output? What is the maximum value as the output? What is the maximum input? What is the common mode range? So if you look at the given condition, I'll go back to here. VDD is only, let me see what VDD. VDD is only 1 volt. So VDD here is, and VSS is also, so which means if you have a 10 millivolts input, your output is not going to be 6 volts because the maximum is what? 1 volt. So it's clamped basically. Well, that's what we call it. So the output will never be more than 1 volt. And in fact, it will be less than 1 volt. And then we'll look at why. Okay. So now let's look at, okay, so you guys might say, okay, how do you get A1 and A2? Well, this is something we have studied earlier. But if you really wanted to look at why, you can draw the pi model for this type of transistor. It's very easy because you have the input and you have the output and you have the load device. Or for example, for stage 1, you have GM1 times V in. So this is V in here. And you have RO, RO2 or RO1 either way. And then you have this RO4 is the current source, right? And for the second stage, you have VO1 coming in. And you have RO6 is a, and then you have RO7 is the current source. So in this case, you can easily calculate, for example, in this case, VO1 is V in times GM, right? That's minus, and then times RO2, RO4. So by dividing V in on each side, you get gain of second stage. For the second circuit, you have VO equal to GM times VO1 times RO6 in parallel with RO7, and then get a minus sign. So this is how, I mean, you can easily go back and forth, join the equivalent circuit and join the external resistance. You know, this is internal resistance, and then this is a current source. And here you do the same thing, you get the gain. So now the next step is we're going to look at the range. Okay, so I know this is the most confusing part because I think the most question I got is what is a okay, so again, step 9. So maximum VCM and minimum VCM. So this is common mode input and common mode input, the range. So without the circuit, it would be very difficult. I mean, let me go back to the circuit and then we'll see. So if you look at this one here, common mode input is applied over here. So at what time would you have maximum that this thing is no longer working? Right? So by looking at this, you say, well, if Q5 is not providing the kind of current that I need, if Q5 is somehow, what happens with Q5? It does not supply the current, and then the biasing is lost. If the DC biasing is lost, you no longer have amplifier. That's where your circuit would experience the maximum input voltage. So at what time would Q5 lost the capability to provide current? Is Q5 goes into a triode mode. It will never go off. It will go to triode mode. If Q5 goes to triode mode, what is the voltage between the source and drain of Q5? For MOSFET, 0.2. So if that's 0.2, how much voltage we have here? 1 minus 0.2, you get 0.8. And 0.8, from 0.8 to here, we need a voltage drop. That voltage drop is VGS minus VT, maximum. That's 0.2. So from 0.8 to 0.2, yeah, that's how you're going to get your voltage. Let's see, Q5 level saturation. And you get 0.7, sorry, 0.7, yeah. So we get here is Q5 leaves saturation. And so when Q5 leaves saturation, we D5 is going to be 0.2 volts. So we D at the amplifier with D1 is going to be 1 volt minus 0.2 gives you 0.8 volts, 0.8 volts. And so this is 0.8, and then VCM max has to be, let me see, what symbol do I call it? I want to make sure I have the correct name. This one we have, we S1, sorry. So we S1 over here is 0.8 volts. So we S1, oops. We S1 0.8 volts. And this one, we max will be we S1 minus VGS. And VGS is going to be 0.8 minus VGS. So VGS, remember VGS is VT, sorry. So let's do it this way. So VOV is VGS minus VT, fine. So VGS is going to be VOV plus VT, and VOV is 0.2 and VT is 0.5, so we get 0.7 volts. So now we plug in this number here, 0.7. So we got VCM max equal to 0.8 minus 0.7 equal to 0.1 volt. So that's what we get for the common mode max 0.1. So this is interesting is that we're looking at maximum input. So if your input is exceed 0.1 volt, the circuit will no longer amplify because Q5 is no longer providing the current source needed to bias the circuit. So for VCM mean, and yeah, I hate this blackboard stuff. You know, we have to go back and forth too. So for VCM mean is that we need to look at is this. If this is too small, what happens? This is too small means too low. This is too low means this thing at your Q1, because this voltage here is fixed. You see, this is -1, right? And this is -1, and then for this VGS, we need minimum of 0.7, right? VGS 0.7. So VGS 0.7. So this is -1, minus 0.7. We got -0.3. So this is -0.3. If this voltage is too low, apparently the difference between here is not sufficient to maintain the circuit in operation. So this one will leave saturation. So therefore, the minimum voltage has to be above this is -0.3. Okay? So we're going to say, so this VD -0.3, and that's what we're going to get. So VD1. So yeah, so we S3 equal to VD3, which equal to minus 0.3 volts. We just analyzed minus 0.3 volts. Yeah, and then so this VCM mean has to be S3 minus 0.5, so minus 0.8. So S3 VD1. So VD1 minus 0.5. That's the minimum. And then 0.5, 0.3 minus 0.5. It gives you minus 0.8. So that's your common mode input range. This is where if you look at the circuit again, we go back to the circuit again, is that this is -1, and this is 0.7 for VGS. So this is minus 0.3. 0.3 minus 1 is due to 0.3 volts at VGS. This is minus 0.3, and this is the drain of the other circuit. From this to drain, it can only drop maximum 0.5 volts. That's your VT 0.5. So minus 0.3 minus VT, so that gives you minus 0.8 volts. So now you got the input common range is between 0.1 and minus 0.8, minus 0.8 to 0.1 volt. So that's your range. Okay, so we got the range to be minus 0.8 to 0.1 volt. Now, this is only your input range. It doesn't mean that you will get a sinusoidal output. So that's why the next step is we need to go to look at the output max. If you look at the maximal output range, we need to go back again to the circuit to look at what condition, this is your output here. Forget about the capacitor. So this is your input, this is your output. At what condition would this circuit like operate in terms of no longer amplifying? Well, first of all, you can see like what happens if Q7 goes out of saturation. If Q7 goes to triode, what happens? You lose the biasing current of Q6. So therefore, your VO output max will be when Q7 goes out of saturation. It goes to triode when Q7 is in triode. How much voltage drop from like for VDS or Q7? 0.2, right? So therefore, your output over here, maximum how much you can get? 0.8. So 1 volt minus this guy, so 0.8, that's your maximum output. And what condition would this, like if this output is too low? Now, of course, right now we're assuming whatever we have here. We're just looking at what the maximum we can get. So if we get there, the maximum is 0.8. If this guy go into trial mode, what happens? Yeah, that's when it goes to no longer amplify. So therefore, your output over here will be -1 minus or plus 0.2. You get there is 0.8. So we can say that 1 Q7 leaves saturation, and then VDS7 is 0.2 volts, or SD7 in this case. I think we better to SD7. So therefore, VO max equal to 1 minus 0.2 equals 0.8. And for minimum is 1 Q6 leaves saturation, and VDS6 equal to 0.2. So VO equal to -1 plus 0.2 gives you minus 0.8 volts. Okay, so now we got here, we got the range. So the range is minus 0.8 to 0.8. So remember in the in the previous page, we got this input range is between minus 0.8 to 0.1. And then now we get, that's the input range, common mode range. The output range is minus 0.8 to 0.8. But the fact is that if your input is too big, like a previous example we had, if it's 1 millivolts, your output is already 0.6 millivolt. I mean, your output is already 0.6 volts. But if your input is more than 1 millivolts, like 2 millivolts, your output 1.3, which is impossible. So in that case, your output will be clamped at 0.8. So if your input is small enough, you get a sinusoidal output. Your input is too big, at your output, you get a clamped. So it's no longer going to be, like if your input is small, what you draw here is that if your input is small, your output will be sinusoidal. But if your output is big, you got something like this. So this will be clamped at 0.8 volts. So you're no longer going to get everything like sinusoidal. The top part is clamped. Okay. So that's example 9.6. And now we're going to go into example 9.7. So last week or the week, we found the DC biasing condition for this circuit, and we went step by step, so we're not going to repeat that. But what we need when we do the gain calculation is we need to know the current of each transistor, and also we kind of have to know the beta of each transistor. But when we did the DC biasing calculation on this circuit, we basically assume beta is infinity. So this is interesting. When you calculate the BJT, sometimes we assume beta is infinity, and sometimes we don't. We cannot. So what happens is that because when you do the DC biasing, beta does not make a huge difference. It's only 1%, because beta is typically 100. So beta over beta plus 1 is 0.99, right? So it's 1% difference. So for DC biasing, so often you can neglect the beta. Just assume it's very big. But when you do gain, you got to have beta, because beta cannot be infinity. If it's infinity, and you got infinity gain, which is not the case. So for small signal, you can never neglect beta. So beta has to be there. Otherwise, you cannot get your gain. So this is where I wanted to just to look at maybe before I go to the circuit, I want to do a review of these two things that'll help you to understand. Okay, so to understand why in the book, in the example, they said, oh, by observation, or sometimes by inspection. So basically, they assume that we're all very proficient in circuit analysis. Well, just by looking at circuit, you know what it is, right? So, but I know that many of you are not able to do that. I mean, at least in the beginning. But maybe after doing again, all this homework, you'll be able to. But in the beginning, definitely not. So let me do a few quick catch up on the things. Just a few things starting from here. Let's say you have a common source, a common emitter amplifier, because this is BJT, so we're gonna look at common emitter. So for common emitter amplifier, let's do it this way. So for this circuit, we did this like 100 times already. So you can draw the equivalent circuit to be neglecting that R1, RO. So we have R1 here. So for this one, it's very easy to get VO equal to minus GM times V in, and then times R1. So your gain is going to be minus GM times R1, right? So that's very simple. Now, this is R1 is the top, the collector resistance. What happens if I have, say, I cannot neglect VA, I have the resistance that I have to consider. So in this case, yeah, you would simply add RO over here, and your gain will become, with RO, your gain will become minus GM times R1 in parallel with RO, right? So that's very simple. You got it. And for the, so now also in the book, for the future analysis, they said, well, this is okay. This is very easy. But when this circuit gets bigger, gets multi-stage, this circuit sometimes doesn't really do what we want to do. So they use the T model. We normally don't use T model for common emitter, but they did anyway. So for the T model, you can draw this circuit like this. Okay, so we draw the T model, and then we have this one, we in come in. But for the T model, the trick is that if you look at V in on this one, so V in is the current times RE. You got V in over here. So what we need to do is instead of using that GM, we're no longer going to GM, so we're going to use IB. If this is IB, how much is on top at the collector? It's going to be that beta times IB. And then how much current at the emitter? So it's going to be this, right? So let's do it this way. So now we have V in equal to 1 plus beta times IB times RE. And how much is VO? How much is VO? Can you guys tell me? So VO apparently is minus beta times IB times R1. So now we can have the gain equal to VO minus V divided by V in. The beta is going to, that IB is going to cancel, and we get minus beta over beta plus 1 times times R1 times R1 over RE times R1 over RE. So because beta over beta plus 1 is almost 1, so therefore you can basically approximate into R1 over RE. And it turned out that this equation is so beautiful that in the book, they will refer to saying, by inspecting the resistance at the collector and the resistance at the emitter, the ratio between the resistance at collector and the emitter will give you the gain of the circuit. So that's what it is. The current, the resistance at the emitter, the resistance at the collector and the resistance at the emitter. And the ratio of these two will give you the gain of your circuit. And this is pretty much true for every circuit. For most circuit for BJT, it's always true. So they did this anyway. So if you have an emitter follower, what happens? So remember this emitter follower, we have and you remember already for emitter follower, the pi model doesn't work very well. So we always use T model. So we use T model, the T model becomes this. And the emitter is grounded. So in this case, they will do the same thing. They will do the IB at the gate, and then at the collector, it's IB times beta, and at the emitter, it's beta times beta plus 1 times IB. So suppose there's nothing connected over here. Suppose there's nothing connected VO. You can easily calculate V in equal to beta plus 1 times IB. It's going to be times RE plus RE. And you have V out equal to beta plus 1 times IB times RE. And now you have your gain. Your gain is going to be your VO or your V in. And the 1 plus beta IB cancel. So you get RE over RE plus RE. And remember, this RE is a small value. It's typically like a few hundred or a few 10 ohms. But the RE, the capital RE, is in the kilo ohms. So therefore, that's why this is approximately 1. So this is approximately 1. That's the common emitter. So I want to give you this like a general, the simple review, so that it will help you to really calculate the gain of example 7.7 or 9.7 or 9.8. Okay, so let's go back to this example 9.7. Oh, okay. By the way, so 9.7. Also, the second part of 9.7 asks you for the total losses. So let me do this. Let me add another page so that I can do the losses. New slide. Okay. All they do, I think they didn't call it loss. They call it power dissipation. So when you do power dissipation, you know how to calculate power? Is the current times voltage. And in this case, the DC, you have 2 voltage source. One is your VCC, other one is VSS, is minus 15 volts. And then so what you need to calculate is total ICC and total ISS. So if you go to the circuit over here, and you can count by hand easily how many milliampere coming out from VCC. You see is Q1, Q2. Don't forget about this. See, this is also Q4, Q5, and Q7. These two are in series. So how many transistors? You have 1, 2, 4, 5, and 7. So how many milliamps? So 1 plus 1 plus 5. Well, also Q8, sorry, not this is series, but this is Q8. So Q8, Q7 is 1, is 5 plus 1, plus 1, plus 1, 8, and then plus 0.25 is plus 0. So 8.5. So ICC is 0.5, 8.5 milliamps. Okay, so how about this one? Should we count this one? No, apparently not, because they come from ground, not VCC, so don't count it. Okay, don't count this one. So now we count ISS. ISS 1, 2, 3, 4, 5. It's very clear. So 1, 2, 3, 4, 5. So we have 5 plus 1 at 6 plus 2 is 8 plus 2. So we get 9. So ISS is 9 milliamps. So your power will be ICC times VCC plus here we're going to use the absolute value. So VSS times ISS. You're going to get 8.5 times 15 plus 9 times 15. And getting 200 something. Now, one of the important things is that don't use minus sign here because the voltage coming in to minus 15. So this actually delivers power. Okay. So this is sinking power, right? Remember, current coming into a negative voltage source. This actually delivers power to the circuit. So these two are adding, not minus each other. Okay, so that's important to understand. Okay, so now let's get into the business of doing the game. So for the first stage, you also ask for the common mode range. Okay, let's skip that one because that one is not so much important. I want to get to the game. So for stage 1, in the book, it will say, okay, by inspection, we can find the gain is going to be the resistance at the emitter, the collector, and the resistance at the emitter. And they study also by looking at the input resistance. So in fact, if you have a doubt at this time, you can start with a pi model. So if that makes your life easier, do that. I'm going to do the pi model. Okay, anyway. So this is, should we look at the circuit? What they did is they really add, because at the output Q1 and Q2, we connected the output, we connect to the second stage. So we don't know what the second stage is going to do. So what we're doing is we simply take the input resistance connected over here. So by calculating input resistance second stage, we can now calculate the gain, which is from here to here is VO, let's call VO1, right? So if you look at this circuit, and can you tell me what is like what is the, oh, something is strange. It doesn't go to where it wants to go. What is the R, like R input, or they call it RID. So if you look at the circuit over here, if this plus minus, so which we ID over, let's call it IID, which will be simply R pi 1 plus R pi 2. That's your the first stage. And remember, second stage is the same. If you look at second stage differential amplifier. So therefore, we can easily claim that Ri2 equal to R pi 2, which, let me see, which is R pi 4 plus R pi 5. That's your Ri2. That's what we get. So at this point, what we need to do is we need to find out what is R pi 4, what is R pi 5, and also we need to look at, we also need to get the gain from here. So if we look at the gain, is this is GM times 1/2 VID, and this is GM times minus 1/2 VID, and this is R1, this is R2, and we can okay, I have to add a page. I don't have space. So I'm going to add another page. So looking at this circuit carefully, the secondary and primary basically really decoupled. So only middle part is the output. Okay, so I'm going to write the middle part. That's the middle part. This is minus. The other side is minus. To do this, you can do nodal analysis by doing these two nodes, or what we can do in an easy way, we can transfer this, use source transformation. We can transfer this one and then put it into a voltage source. So actually, I get the wrong sign. It should be down. Okay, so I'm going to redraw this one into a voltage source with a resistor. And this one too, with a voltage source and a resistor. So this current coming out this way, coming this way, R2, R1, and RI2. And this is GM times VID over 2 times R1. This is minus GM times VID over 2 times R2. So now I can find out easily what the VO is, because now I have really just the 2 voltage source in series and 3 resistance. So I can have VO equal to the 2 voltage source. By the way, they are same direction, but one is positive, one is negative, so they actually added. So it's going to be R1 GM VID over 2 plus GM VID over 2 R2. That's the voltage divided by R1 plus R2 plus RI2, and then multiply by IR2. So we got this voltage. Now by dividing VID on both sides, okay, and you can get the gain. So basically, if I'm doing it here, so A equal to VO over VID, and it's going to be 1/2 GM. I take that out, and the top is going to be R2 plus R1 times RI2 divided by the bottom is R1 plus R2 plus RI2. So if you inspect the resistance, what do you get? The resisted part. That's really, I can rewrite this one into very simple format. Is GM divided by 2 times R1 plus R2 in parallel with II2. So by doing this equation exactly same as it in the book. Okay. So and then we can find the gain quite easily. But in order to find the gain, of course, we have to find a few other values. Let me Oops. Okay. So now we have the gain written, but we have to calculate also, like in this case, we need to calculate R pi 1, R1, R2 is given, and but Ri2 is not given, so we have to calculate R pi 1, R pi 2, to get our ID, and we not to get R pi 4 and R pi 5, to get Ri2. And we also have to calculate GM. So I already calculated here. So our R pi, so our GM. So GM is IC over VT. And apparently this IC over VT, IC is 0.25 milliamps for the first stage, divided with VT is 25 millivolts. We got 10 milliamp per volt. And for R pi 1, we have beta over GM. So beta is 100 over GM is 10 milli. So we have milliamp per volt. So we have 10 divided by, so we get 10K. So R pi 1 is 10K, and R pi 4, I calculated, let's see. R pi 4, I calculated is 2.5 kilo ohms. So Ri2 equal to R pi 4 plus R pi 5 equal to 5 kilo ohms. So if you review the book has 5.0 something. Okay, that's because they assume the current is in the emitter, not in the collector. But over here, I consider the collector and the emitter has the same current. So therefore, I don't have that 0.52, but it's 0.5. So Ri4 is 5K. So that's what we get. So by plugging all these numbers, we can get the stage 1 is going to be 1/2 GM1 times what we get is R1 plus R2 times Ri2 divided by R1 plus R2 plus Ri2. So we get 10 over 2 times, I believe this is a 20 kilo ohm plus 20 times 5 divided by 20 plus 20 plus 5. And that gives you 22.2 volt per volt. That's a first stage gain. So you look at here. So the key is to calculate R pi 1, R pi 2, which it doesn't do anything with the gain, but only calculate the input resistance. But for we need to calculate R pi 4 and R pi 5. We need to calculate GM1 and GM2 so we can get the gain over the first stage. And for stage 2, this is another differential amplifier. So for differential amplifier, but it's a single-ended. So we can like use what the book says. You can inspect the resistance, and then we have A2 EQ calculated to be. I mean, you can also you can use the first equation that we derived from other circuit. In this case, will be R3 times Ri3, R3 plus Ri3. The reason we can do this because this is 0. So R here is equal to 0. So therefore, by the equation from the previous page, you would simply remove that R, the one with R, you get this one. So by plugging here, the GM is also different. So GM in this case, GM is going to be IC5 over RC5 over VT, which is going to be RC5 is how many milliamps? 1 milliamp times 25. So you got 40 milliamp per volt. So A2 plugging here, you got R3, and everything you got here is minus 60 volt per volt. So we got this one. But over here, of course, this important thing is I3. How do you calculate II3? We need to go back to the circuit by, again, inspection. So the inspection here, I'm not gonna, we don't have time here. And then we can go to stage 3. We do the same thing. For stage 3, stage 3 is a common emitter amplifier because the emitter is grounded. However, there's resistance at the emitter. That's the only difference. If we don't have R4, this will be purely a common emitter amplifier. But with R4, there's a little bit difference. So again, over here, the first thing we need to do is to identify R5. But R5, you guys can review the book. It tells you how to identify R5. Once you identify R5, you can get the gain of 3 is going to be R5 in parallel with R4. And RE7 plus R4. See, these two are in parallel. And if you draw the circuit, if you draw the circuit, it will look like this. Remember, this is your output, and this is your RE7, this is your R5, and this is your R4, this is your input. And from this circuit, you have IB here, and you get this beta times IB, and you have this is beta times IB plus 1. Okay, so then you really can write like VO equal to R5. Oh, R5, there's also RI4. So VO is R5 times RI4 in parallel times 1 plus beta times IB. So that's your VO. And your VIN, see here, your VIN is here, is beta plus 1 times IB times RE7 plus the other two in parallel. So, so here, again, you can get the gain, right? So plugging this back, you get this gain. And by doing this, we find the gain is going to be minus 0.6242 volt per volt. Okay, and the last stage is emitter follower. And we already derived how to calculate the gain of emitter follower. Just at the beginning of this example, I had is RE6. Yeah. So once you get that number, so F4 is going to be, I mean, almost 1. So this is really R6 over R6 plus RE8. And RE8 is very small, which is in this case is something like 5 ohms. But R6 is 3K, right? 3K. So anyway, so this gives you almost 1 plus 1 ohm plus 1 volt per volt. So your final gain is going to be A1 times A2 times A3 times A4 because each stage is in series. So you get the gain all the way. This is positive, this is negative, this is negative, this is positive. So final number is positive. We get 8,513 volt per volt. So this amplifier, this 4-stage amplifier, has a huge gain, 8,500. So if your input is 1 millivolt, your output will be 8.5 volts, which is possible in this case, okay? Because your input is 15, your VCC is 15. So it is actually likely you can get the actual number you want. And we also have to calculate the output resistance in the circuit, which you simply go back to the common emitter amplifier, how we calculate the output resistance. And by doing the circuit, you can also do the equivalent circuit. If you do an equivalent circuit, and what you need to do is you need to find out what is this one, this R5, okay? And then this your output. And you apply Vx over here, and you get, sorry, Ix. You apply Vx, you get Ix. So your RO is Vx over Ix. And you can write down. So if this is a IB, and this will be 1 plus beta times IB, and this is beta times IB. So you can easily identify each of this voltage and current. So now you can find out, and this final resistance it's a quite interesting number. It's R6 in parallel with RE8 plus R5 divided by beta plus 1. And this number. And RE8 we calculated also already, and this 152 ohms. So the common emitter amplifier is output resistance very small and input resistance very big. And then so this is what we get for the common emitter. So in this case, let me also do one more thing, is that you can find out what is maximum output and what is maximum input range. So for the maximum output and maximum minimum maximum output range and maximum input range, what we need to do is we simply go back to the circuit, and by looking at which one goes to, like for example, this is the maximum when this is going to saturation. When this goes to saturation, this is 15 minus 0.3, you got what? 14.7 volts. That's your maximum output, right? And for maximum input, if this goes to saturation, this becomes 0.3, and this becomes 14.7 minus 14.7, and this is your like a minimum input. So that's like a minus 14 volts is your minimum input. So it's easy just by looking at the circuit, identify which one is going out of, in the BJT case, is which one goes out of saturation. Yes. The second stage? Yeah? No, you mean here? I will post this tonight, so you will have the slides noted. So, excuse me. So Wednesday, we're going to start chapter 10, frequency response. But I'll give you a week to work on this. So next Monday, we're going to have a quiz. Basically, based on I know this is very long, so the quiz won't be that long. Because your quiz that will be that long, it will take the whole hour. That's not good. The quiz will be shorter, but you need really to get familiar with what we're talking about today. It's how to calculate gain, which stage, how to calculate input resistance, output resistance, and all that kind of stuff. Okay. Any questions? Okay, we'll see you on Wednesday. Next week. Not Wednesday. No, Wednesday, next week. Today I lost my phone at the gym. I was stolen, so I can't log on campus. I went to Verizon. Yeah. And I filed insurance, so they said it would take 24 hours for me to get. Oh, okay. So I may have to play. Oh, okay. I can access campus because it sends you a text message for me to log back on to my SDSU and campus. Oh, okay. So basically, I locked out. Okay. Yeah, if you need my help, be happy to do that. Yeah.